Okay, this is Griffiths problem 2.4, continuing with problems about infinite square wells. I think there's 9 total problems about infinite square wells, and they are a very important problem to really get down. So, as promised in section 2.2, where we talked about infinite square wells, I mentioned that whether you get a sine or cosine is going to depend on if your well is centered or not. Now, personally, I just prefer to have, I think it's easier to have our wells sit on A and 0. But a lot of textbooks, and I mean, if you're doing the problem in the real world, you can pick and choose whichever way you want to do it. Some people prefer this, other people prefer the way the example was done in Griffiths. So here's our potential as a function of x, and now instead of our potential well starting at 0 and going to a, now our potential well is centered around the origin, and it goes from negative a halves to positive a halves. And these boundaries are where the potential goes to infinity. Inside the square well, our potential is equal to 0. So that means that we can use our Schrödinger equation, which was our time-independent Schrödinger equation. I should specify that we have here plus v psi equals e psi. Now I'm going to go ahead and move all the psi's over to one side. Now I have v minus e psi. Our v equals 0 inside the well. So over here, our psi is equal to 0. The wave function does not exist outside the well. So I get h bar squared over 2m d psi dx squared equals negative e psi. Doesn't matter which side you like to keep the negative on. For some weird reason, I like to keep it on this side. And then we have 2m h bar e psi. Okay. Now, here we have the second derivative of the function equals a negative some constant of the original function. What satisfies that is going to be a sine or a cosine. Both sine and cosine satisfy that condition. Now I'm going to say, so our wave function has some constant, some normalization constant. That constant will stay when we take the derivatives. So our constant will be over here on our left-hand side as well as over here on our right-hand side. So our constant's going to cancel out no matter what. The reason we put it in there is for normalization. Now, if I take the derivative of this, instead the constant stays the same, we take the derivative of the inside, kx is just k. Oh, and then I get cosine. So the derivative of sine is cosine. The derivative of cosine is negative sine. Then if I take the second derivative, now I'm taking the derivative of the cosine, so I have the A just stays, and then I have k times k, derivative of the inside times derivative of the outside, and that's negative sine kx, and then my derivative of sine is positive cosine, so that stays negative 2, and then I get a kx, cosine, sorry, k squared cosine kx. And as we can see, that's the same as taking our original function. I could factor out a negative k squared, and they just get negative k squared times my original function. So either cosine or sine or a linear combination of both satisfy that. So we know this. We don't know A or B. We would have to get those from two places. First is boundary conditions. In this case, our boundary conditions are going to tell us if A or B is equal to 0. Or basically if our wave function is a sine wave or a cosine wave. And I'm sure you could have boundary conditions where you would get a linear combination of both, but I don't know why you would set up your problem that way. That just seems silly. So what we have is that k of negative a over 2, psi of negative a over 2 has to equal 0. We also know that psi of positive a over 2 has to equal 0. So I have 0 equals a sine of k times plus or minus a over 2 plus b cosine k of plus or minus a over 2. Now one thing that we do know is that psi is not 0 at x equals 0, because that's the middle of our well. Here, I know that there isn't a condition of sine that leads to that. So sine of anything equals 0 at kx equal to 0 or kx equal to n pi. So there isn't really a way for me to get a sine to be equal to 0 easily there, because our sine has to be 0 at kx equals 0. K can't be 0, otherwise we would have our wave function equaling 0, and that would be constant. So k is not 0. We know that our wave function is not 0 at 0, so that leaves us with a equals 0. Meaning that 0 equals b cosine of k plus or minus a over 2, and cosine is 0 at kx equal to any multiple of pi halves. I kind of ran out of room. Let's go down here. At kx equal to 2n plus 1 pi over 2. I put that in there so that we know that it's always an odd integer. So if we graph this out, we have our cosine looks like this. So cosine of 0 is 1. Cosine of pi is -1. Cosine 2 pi is 1 again. And it is 0 at pi halves. It is 0 at 3 halves pi. It is 0 at 5 pi halves. As you can see, that's already more complicated. That's why personally I prefer the sine wave. But yeah, there we go. It is fine either way. So what we have is a equals to 0. Our wave function is some constant b times cosine kx, where we know that kx or k is limited in that way. Now we want to check that our allowed energies are fine. So we want to check that our allowed energies are consistent with what Griffiths got in equation 2.23. And then you want to confirm that the size can be obtained the same way. And that's kind of a fun thing. So first, let's check the energy levels. So our energy levels, we have kx equals some odd integers. So you can just even specify that needs to be odd. Or we could do probably maybe something like, I don't want to use n again. I guess it's fine. We'll just keep it with n. There we go. Our odd number there. And, oh, actually, yeah, that works out. Okay, so let's go ahead and plug this in here. So we'd have k at the boundaries, plus or minus, equals this. We can go ahead maybe to, let's make it a little bit easier. Let's just call it L. So then I have k times a equals some odd integer L. Or I have k equals L odd integer over a. And then if I look back at my original equation, I had d psi dx equals -2m over h bar squared times e psi. Or if I do it in terms of my k's, like up here, I have this, meaning that my k squared is equal, oh, sorry, that's not a pi, that's 2m, equals 2m over h bar squared times energy. Or my k equals square root of 2m times e over h bar. So I have square root of 2me over h bar equals my integer L Don't get too attached to L. It is used for other quantum numbers. You could just use an N. It just kind of annoys me. I want to keep it straight that it's odd. Now if I want to solve for energy, we see that we get pretty much the same exact thing that we had for our other energy levels. Oops. And h bar squared over a squared 2m. Same exact formula we got before. Yeah, pi squared. Okay. Whoops, we can double check. Against what he had here. And there we go. Same formula for the energy. So it really doesn't matter which one you do. You could do an L instead of an N instead of L, by the way. It really doesn't matter if you choose a sine or if you choose a cosine. You're going to get to the same answer at the end of the day, either way. Okay. Now, the next part of this question was saying to confirm that the size can be obtained from this equation 2.24. Right here. So this is the quantization part, is that we have some psi in, some in number of psi's corresponding to each one of those levels. So what we have is a cosine, what he had is a sine. And we can go ahead and just keep that normalization that he has. So that's sine in pi over ax. Oops. Sine in pi over ax, whereas we had something very similar. I'm just using L. Our normalization would come out exactly the same. At any rate, that's not what the problem is asking. And then we just have some cosine of L pi over 2a x. So if you like, you can just simplify out that the L's are just always odd. Okay, or we could keep it as n's if you really like the n's. So now to find that that works the same way as before, let's go ahead and just look at this normalization. So that's the probability that we find our particle anywhere in the space. In this case, it would be between a half and a half. So I have 1 from negative a half to positive a half dx, and I should really include the absolute value of b squared cosine squared kx. I'm just going to keep it as k so I don't have to write all the other stuff. Now, so I want to show that I can get this from this, basically. or even just from this. So we start here, we want to get there. Now we're going to do what is rapidly becoming my favorite thing in the world to do. I'm gonna go ahead and integrate this bad boy by parts. So we have u dv equals uv minus v du. Okay, my u is going to be cosine kx, making my du negative sine kx. Since I chose u to be cosine, that means dv has to be cosine kx, and then v is the integral of that, which is just going to be positive sine kx. Now I can go ahead, rewrite this guy again. So I have 1 equals absolute value b squared, and I'm going to have u times v cosine kx. So that's my u, my v, sine kx, evaluated at these boundary conditions, which we know make it equal 0. And then that is going to be minus the integral a half to a half dx, and now we have v, this guy, sine kx times du, which is negative sine kx, making that positive. And there we go. We have the same normalization constant. Isn't that nice? So we got it from the same exact way that the book did. Sine is even, we can go ahead and take that from 0 to a half, whatever we want to do there. But we get the same equation as the book. Same equation as the book, but different limits. Same width though. So since the integral is the area under the curve, since the width of this is still a, we will get the exact same normalization constant because we're doing the exact same integral. Isn't that fun? Okay, and that's it for problem, I already forgot what number that was, 2.4. So there's our first solution, and there is the second part.